Hello and welcome back to Survey of Bio, and we're going to continue our discussion of enzymes with a quick review. So if you remember last time we talked about the enzyme substrate complex and how that every enzyme has a specific active site that fits one substrate. So in the case, if you look here, we're going to talk about sucrase, which is the enzyme that breaks down sucrose. So we have an enzyme that will, in the purple, that will bond with a substrate, in this case sucrose, and that forms the enzyme substrate complex right here, there. And so in that formation, if you look, the bond right here is slightly bent. It's put in a very unstable position that makes this reaction more likely to happen. That's what an enzyme does. It lowers the activation and makes the reaction more likely to happen. So it's a hydrolysis reaction in this case because we're breaking it down. So we add some water. So the substrate is converted to products, which in this case are fructose and glucose. So we've broken that down, and the enzyme is then free to go and carry out another reaction. So if you remember, the enzyme is not changed during the reaction. So enzymes are very specific. So here's a little cartoon where this E-shaped enzyme is going to take glucose and fructose, and in this case it's going to take the two individual monosaccharides and it's going to have a condensation reaction where we're going to link them together to form sucrose, so kind of the opposite. So the glucose and fructose will fit into that active site. It's very specific. So we have an example where we can have starch and cellulose, which are both polymers of glucose monosaccharides. So they're very similar to each other. So they're very similar. But different enzymes are needed for each one. Okay, they're very specific. So even though starch and cellulose may look very similar, different enzymes will break those down. So now we get into a little bit of the new stuff in terms of we have an active or functional protein. Here's our enzyme. Well, what happens if the conditions aren't just right for it? So specifically in this case, what happens if we heat it up? So what happens is there's a three-dimensional shape change and the protein becomes inactive. We say that it's denatured. So heat and pH are the two big ones that we're going to talk about. But what happens is they produce a three-dimensional shape change, and the protein becomes inactive. So not only are these enzymes very specific in terms of the substrate they react with, they're very finicky, if you will, in terms of the temperature and the pH that they can perform under. So this shows the same thing, that if we have our normal protein that's highly folded, it's got a specific shape, that if it becomes denatured, it kind of unfolds and we get this ribbon. It doesn't work. So the big ones that you've got to remember in terms of conditions that will affect the function of a protein are temperature, pH, and then the other one is heavy metals like lead, cadmium, or mercury. So it's very important to realize that these proteins, if they're not within a certain range, they're not going to work very well. So heat is the first one. So every enzyme has an optimal temperature. Okay, that's the temperature that they work best at. So if you look at the graph over here on the left that shows temperature versus activity, it has a peak right here. And above and below that temperature, the enzyme doesn't work as well. So if we start here down at a very cold temperature, down here, initially the heat boosts the enzyme activity by increasing the molecular motion. So as we go up, the enzyme activity will increase until we reach kind of the optimal temperature. So at that point, the temperature will denature the enzymes. So at this point, the enzyme will fall apart and we rapidly get a decrease in the activity. Now, at cooler temperatures, before the optimal, the enzyme isn't denatured, it's still function, it's just slower. The molecular motion isn't as high, and so cold temperatures will slow down the reaction. It won't stop them because the enzyme isn't denatured, but it just slows them down. So here's another graph that shows that very well. So if we start over on the left at a very low temperature, as we go up, the rate of enzyme activity increases because the enzyme is working. That's through this area of the graph right here. The enzyme is working, but at low temperatures it's much slower. And when it reaches its optimal temperature right up here, that's when it's at the highest. And after that optimal temperature, it quickly declines. The activity quickly declines because the protein has been denatured and the active site isn't available to the substrate anymore. The second one that we'll look at is pH. So if there's a rise or fall in the hydrogen ion concentrations, okay, this affects the active site and can denature enzymes as well. And so just like temperature, every enzyme has an optimal pH at which it works best. So here's a couple graphs so we can look at chymotrypsin in the upper left hand here. This is an enzyme that works on breaking down proteins, and it works in the small intestine, so the optimal temperature is near 8. Now pepsin, right below that, is another enzyme that breaks down proteins, but it's found in the stomach, so its optimal temperature is much closer to 2 because of the acidity of the stomach. So these two enzymes, chymotrypsin and pepsin, both work on the same substrate, proteins, but they have very different pHs because of where they're found. So we can see in the upper right hand corner, cholinesterase, that has very limited activity below a pH of 6, but above that it stays about the same. Papin is another enzyme, and this one is functional across a wide ranges of pH. It's not as sensitive to the pH differences that we see. And here's another one that just shows kind of the bell curve. So we have our optimal pH, and above and below that, pHs will denature the enzymes and they will stop being functional for that reason. And here's another one that we talked about. We had talked about pepsin and chymotrypsin, but here's trypsin was very similar. So both of these are proteases. Both of these are going to work on denaturing proteins and breaking them down, but one has an optimal pH very close to 2. The other has the optimal pH much closer to 7. So this goes back to the specificity of these enzymes and how well they work for that. So knowing that now, I'm going to show you a quick animation that will kind of illustrate how all of this works.
An egg provides a good example of how heat can change the structure of proteins. Proteins are found in both the egg white and yolk, and these proteins have different structures in raw versus cooked eggs. Let's consider the proteins in an egg white. In their native uncooked state, the proteins are chains of amino acids that fold into complex shapes. Several types of bonds form between amino acids in a chain, stabilizing the structure of the protein. When the egg is cooked, the heat makes the molecules vibrate. The bonds linking the amino acids in chains are strong covalent bonds that withstand the heat. However, most of the bonds that stabilize the three-dimensional structure of the protein are weak bonds, typically hydrogen bonds, which break, allowing the proteins to unravel. When two unfolded proteins make contact, they form new bonds with each other. A large net of interconnected proteins forms, and the egg hardens. Light can no longer penetrate the egg, which is why the clear portion of the egg turns white.
So that is kind of the second one on enzymes and how they can become denatured and inactive. So again, thank you for your attention, and we will see you in the next section shortly.